Hi everyone. Unfortunately the next video in the direct current control series has been delayed a bit, but I didn't want to leave you guys hanging any longer, so I thought I'd make a shorter video about the inverter that I've been playing with recently that I made a little while ago. So let's get right into it. So I made this inverter a little while ago, and I never actually really got to play with it much, because the moment I finished building it, I got given this inverter to play with, which is probably, I feel like overall the design's maybe a little bit better, but it's got very expensive high-end components like these silicon carbide MOSFETs. So I've been playing with this for a little while, and this is actual work I have to do for Formula Student, whereas this one is purely for personal use. But yesterday I dug it back out because I needed it for something, and I thought while I'm waiting for parts for my next video on direct current control, I thought while I've got this out I might as well show you guys it. So I'll start here at the front. So this front panel's got, a load of things that I thought would be useful to have. You've got a power switch, so this is for the low voltage supply. Turn that off and there's nothing going on inside here at all. Then when you turn it on, the blue LED comes on, the blue indicator, and that's just to say there's a low voltage supply. It doesn't necessarily mean the output's turned on or anything like that. Then moving right, we've got a 3.5mm headphone jack, which you'll see why that's useful later. The green button connects directly to the reset pin of the microcontroller that's inside it, which is just useful to have if you need to reset stuff. Then the thing that made this most useful compared to previous iterations I had is that this has got 3 analog inputs on pots and then 3 digital inputs with buttons. I had previous iterations of this that were basically just the microcontroller and some MOSFETs, and it just made it a bit tricky to adjust speed and stuff like that, but now I could have, for example, output frequency, output duty cycle, and output dead time, or something like that. Then the green indicator is for when the high voltage relay is closed. So that's software controlled, so right now I have it mapped to this button, so when it's all powered on, press this button, it closes the high voltage relay. And then the red indicator will come on when the voltage is above about 5 volts on the high voltage side. That's fully isolated. I have this red button as well, which is meant to be an e-stop, but I think the contacts in it are broken, so right now it doesn't work. Now heading over to the back, from left to right again, we've got a ground input which is just connected to the case. Then for the low voltage side, there's 2 ways to power it. You can either power it from a barrel jack, so that would just be like a 12 volt power supply, or you can power it through these binding posts, which is what we're going to be doing. Then there's a fuse for the low voltage side, and the low voltage input should be in the range of about 7 to 20 volts, but the internal regulators get pretty toasty, so I run it pretty much as low as I can get away with, which is about 7.5 volts. There's definitely a few things on this design that I'd improve. That's the first one. I'll show you more once we're looking inside. Then this connector is a bit hard to see, so I'll adjust the exposure. There we go. So this is an Ethernet port. It's not actually, it's RJ45, it's not Ethernet. This has just got all the pins I need to program the microcontroller, and also a few extra ones for analog inputs, and there's also a digital output that shows whether high voltage is present. Then we have our high voltage input. So when I say high voltage, right now it's limited to about 200 volts just because of the caps I'm using. I think the MOSFETs are rated for about 600. And then here's our 3-phase output. And this enclosure I got off RS, and I think it was such a great deal. I think it was priced wrong or something, because they had a whole series of these enclosures, and they were all about 50 quid apart from this one, which was a tenner. So I just got it and made some holes in the front and things, but it's all metal. It's really nice. Anyway, let's take a look inside. So it's pretty much entirely just this one custom PCB that I made. I have a spare here that we can take a look at in a minute. But let's just work from bottom to top, having a look at all the components on here and how it's all connected together. Probably the thing I'm happiest about with this design is the way that it all integrates into the case. So you can see all these grey ribbon cables, they all just unplug and they go to various things. So like this header, in fact this whole module which has got a square around it on the PCB, this is for the audio input. So these 3 wires are for left, right and ground. Just pop that on there, and that means everything can just be unplugged and you pull the whole board out. Overall, I do quite like the arrangement on this PCB. Everything's got little boxes drawn around it, which is nice. It does waste a bit of space though, so I wouldn't recommend doing this unless you've got space to play with. So back to the board, we can start here on the right. This is where the low voltage power comes in through these 2 thick cables. This is just a normal pin header like the rest. And that then comes into these 2 voltage regulators, 5 volt regulator and 3.3 volt regulator. 3.3 is pretty much just for the microcontroller, 5's for a few other things. Most importantly, 5 is the input to all the DC-DCs that I have on this board. So in here is a 5 to 12 volt DC-DC. That 12 volts just for the main high voltage relay, which is up at the top, and one or two other things like the indicators on the front panel. Then I also have 6 DC-DCs here, which are for the gate drives. They also have 5 volts input, and they draw quite a bit. Here you can see the microcontroller. This was the first board I ever did with, well, to be honest, any surface mount stuff. So I was a bit worried to put the microcontroller itself straight on the board, so I bought this breakout board, and that's just socketed with a load of pin headers. Because there's so many pins though, it's very hard to get in and out, so really this should probably just be on the board. It would free up a lot of space as well. And a big issue with using a breakout board like this is you can't get decoupling right next to the microcontroller. The decoupling's all the way down on the main board, which isn't ideal. The microcontroller I'm using is a PIC32 MK0512 MCJ64, I think, something like that. It's basically a PIC32 that's quite high-end, and it's designed specifically for motor control. So it's got a lot of special PWM features, for example, like hardware current limiting and stuff like that. On the left here you can see the RJ45 port that's mounted to the board. So there's a very short Ethernet cable inside here that then goes to the back that you'll see in a little bit. And as I mentioned, that's for programming and other stuff. In here we've got some power LEDs for the 5 volt, 3.3 and 12 volt rails. There's also indicator LEDs on each of the gate drive suppliers. So every supply, all 9 of them, they have their own indicators. I'll turn it on in a little bit and you can see them all light up. When I originally designed this board, it used all through-hole parts and it was very dense and not very nice. There's still a few bits that are hangovers from that. So for example, this enormous relay, which is part of the emergency stop system, and this even bigger buzzer, which was meant to buzz when the high voltage turned on, but it was really horrible, so I've disconnected that. Then moving up, we have our 6 identical gate drive circuits. I'll just talk about one of them. So, for example, this one, we have an isolated DC to DC converter, because the gate drive needs an isolated supply on the high voltage side. This is 5 volts in and a bipolar plus minus 15 volt supply output, which means I can drive the gate both high and low, which is always good. You don't really want to have the gate at 0 volts when it's off in case you get some ringing in a poor board design like this, because then the ringing might turn the gate back on and go over the threshold, whereas if you bring it down to minus 15 volts to turn it off, you're not going to get ringing that's 18 volts or something. Then on the output we've just got, well, input and output, we've just got some caps for decoupling, output LED like I said. There's also a Zener to clamp the output of these DC-DCs. Because they're unregulated if they have no load, the plus minus 15 volt output could become plus minus 18 or 19 volts, which is a bit too high for these gate drive chips, hence the Zener. And what I've done on this board, which is something I like to try and do on all of my isolated boards, is I've just made one line of isolation. So everything on this side is low voltage reference to ground. Everything above that line is high voltage floating. I'm not a fan of boards where there's sort of high voltage and low voltage just sort of scattered around. Even if they maintain adequate isolation, I think it's nice to just put everything in a big line. And that's one of the things I don't like about that Formula Student inverter, is there's just low voltage and high voltage everywhere, which just isn't very good for EMI and stuff like that. You can get capacitive coupling between the noisy high voltage side and the low voltage side, which is meant to be noise free. I'll show you some things I've done on this board to try and help with that further once we look at the PCB. So these 3 massive caps, they're just decoupling on the high voltage side, 200 volt, 1500 mic each. So we end up with 4.5 millifarads total, they're just in parallel. We've got high voltage in, these 2 wires, and then 3-phase output through this connector. I've tried to make the whole removal process toolless, so it's got these weird connectors where you push it in and you can just pull the wire out. Then right up at the top it's a bit dark, but you've got 6 MOSFETs mounted onto the one heatsink, which I think that's probably the part I like the most. It's just, this board, I'm not going to lie, is quite good looking. Lots of symmetry and things, which is normally, there's no point making an ugly board. Most boards can be made nice looking if you care. Then I've got 2 resistors here, so one of them is just straight across the DC input, and that's meant to discharge the caps when they turn off. I've only tested this up to about 30 volts input at the moment, but even that takes about 5 or 6 seconds to fully discharge, which is quite a bit really. But because this resistor is always across the high voltage input, I couldn't make it too low resistance or it'd just get really hot. Ideally, to discharge something like this, you'd have a relay or something like that, so that when the high voltage is disconnected, then it dumps it across a much lower value resistor, and that resistor doesn't have to be rated to be able to withstand that voltage permanently. This resistor on the right is sort of doing a similar thing, but this is just limiting the current that goes through this optocoupler. This is the way that I detect if high voltage is present. So high voltage goes through this resistor and then just goes through the LED of this optocoupler. You can just about see in here some gate resistors as well. I'll try and get a better shot of in here because it's very nice looking. Right, you can kind of see in here. I've got very shallow depth of field though, unfortunately, but there's our 6 MOSFETs, and we've got our gate resistors as well. I think the schematic says they're 4.7 ohms, so... Then looking at the very back, we don't have much more. I've got 2 fans that blow up on the heatsink, mostly just because there was space and I thought it would be cool. They're 12 volt fans, but they're powered from the 5 volt supply so that they're not too noisy. They don't really do that much, to be honest. They're not orientated correctly for the fins on this heatsink. And now we've just got all the rear connections that we've seen before. And here's that rear RJ45. One other thing worth mentioning is this relay at the back. This is the high voltage isolation relay. This, again, it's a nice thing to have, but I tried to mostly use components I already had for this board. And this relay really isn't rated for the kind of inrush currents that you get trying to charge these huge caps. So if I turn this on at 30 volts, the relay just welds itself shut. But I'm very restricted for space in here, and it's mostly just unnecessary, to be honest. Now hopefully you can see this board well, so I can show you all the things I like and don't like about it. Starting off with the thing I like most is definitely the symmetry in the board. I think, it's just really nice. See, as I say, you've got this big line here which separates the low voltage and the high voltage side. The caps are perfectly symmetrical. You've got the MOSFETs at the top, connectors, just especially everything above the high voltage side is almost perfectly symmetrical down the middle, and it just means you get a really nice looking board. And inverters really lend themselves well to symmetry because you're basically just making 3 identical half-bridge circuits. Then hopefully it's also coming across in the camera, the entire of the low voltage side is seriously veer stitched. So I've got a ground fill on the front and the back of this board, and then veers everywhere I can fit them to join the 2 grounds together, and that basically means the whole low voltage circuit is shielded from all the noisy high voltage switching going on. Other things to note on the low voltage side, you can also see this is where the big headers go for the breakout board for the microcontroller. I did purely single-sided load on this because everything's quite spread out, but if you wanted to make this a lot more compact, just pretty much all the surface mount things, just pop them on the back. Especially with decoupling, if you've got the microcontroller on the board itself, what I've been doing recently is putting all the decoupling for the microcontroller on the back. And you can also take advantage of hiding messy components on the back. So for example, this is a board that I've made recently, and this is the same thing, veer stitched, so front and back are ground. And you can see on the front it's pretty minimal. We've just got LEDs, again, perfect symmetry down the middle because I like that. But then this chip needs decoupling, and that is what lives on the back here. So you can sort of see the outline of the chip in these capacitors. This is the decoupling for the microcontroller, decoupling for the other chip, which is a UART to USB bridge. Resistors for the LEDs. There's the header on the back with its caps and things. But yeah, if you want to make a good looking board, put everything you don't like the look of on the back. Coming back to the inverter, overall I think it's a pretty decent design. There's 1 or 2 things that stand out as particularly poor, which are mostly in this upper section. So the first thing is that the gate drive chips are down here, but the MOSFETs are right up at the top, and you want them really close together to prevent ringing and things like that. So if I'd known, I probably would have swapped the capacitors and MOSFETs around. It's always a bit of a challenge, because then if you imagine the MOSFETs here and the caps up here, where does the heatsink go? Because you want the capacitors as close to the MOSFETs as possible. You want the gate drives as close to the MOSFETs as possible. But then the MOSFETs also need cooling, so that's why you end up doing something like this with the MOSFETs on the back, and then capacitors on the front, and gate drives on the front, or something like that. Double-sided is usually the only way to get everything nice and close together. So yeah, that's one thing I don't like, is the distance between them. I think if we look at the back, you can see the traces. So the gate drive traces themselves aren't too bad. You've got one trace going to the gate and then the other one for the source, because it's VGS that you need to control the gate source voltage. So the source just connects to the central point of the bipolar output of the DC-DC, and then the gate comes out of the gate drive. They run up together, sort of routed a bit like a differential pair. Whether that's good or not, I've got no idea. On the back you can probably see the fill a bit better because there's less silk screen in the way. This is the low voltage fill with all the veers, and then high voltage, you don't want any fill. You want everything separated. The tracers for the high voltage side are probably the other thing I'm not particularly fond of. So these tracers are very thin. I'd probably use decent sized fills if I were to redo it. Something like this. So this is the Formula Student inverter. These are the phase outputs, and see, this is just a gigantic fill for A, B and C phase. Something I don't like on this is the asymmetry. This fill's bigger than those ones. I'd probably just bring that down just to satisfy my OCD. But yeah, the high voltage side of this is not so good. So these are the capacitors, these terminals, and then we've got these thin tracers going up to the MOSFETs, which they're probably what limit the power of this inverter, which is a bit of a shame. These tracers are maybe good for like 10 amps, I'm not really sure. You can see on the other side, joining the capacitors together, I have slightly thicker tracers, but then this shows another problem, which is that for some reason I put these tracers right next to each other. So even though the MOSFETs are good for 600 volts and the caps are good for 200, I don't think I'd want to push this much more than maybe 100, possibly 200, because these tracers are just so damn tight. And they don't need to be, because these MOSFET pads are quite far apart, but past me clearly didn't really think about isolation spacing, which is a bit of a shame. One other thing I really do like about this board as well is that past me knew how bad past me was, present me as well, using the right pins on the microcontroller. So every single pin I haven't used has been brought out to a test pad. So that means I can just add loads of bodge wires to connect everything to where it should be. Which I'm afraid to say is actually what I've done on the inverter. There's 4 wires on the back that are joining pins that are meant to be analog to pins that are analog and stuff like that. Because I'm not really using very many pins on the microcontroller, as you'll see when we take a look at the schematic. Trying to think if there's anything else of note. These mounting holes are a bit weird because they're mounted quite far inboard, but that's because they had to be in a specific place for the enclosure I'm using. But yeah, overall I quite like this board, to be honest. It was the first board I ever designed in KiCad, so yeah, I guess it could have been worse. So here's the schematic for the board. Again, little disclaimer that I made this a while ago, so my KiCad skills have improved considerably since then. A few examples of things that aren't very nice: these capacitor labels intersecting with the wire. I'd probably bring these wires out a little bit so that it's clearer what they're joining together. And also I was trying to work out how to do the back annotation between PCB and schematic, and I just kept messing it up. So you can see all of these labels, RA5 goes to RA0, they're all just wrong, which annoyingly means the silk screen on the board isn't actually correct. So I have to keep cross-referencing various different things when I'm trying to work out what test points go to what. But yeah, overall, this shows how few of the pins I'm using, really. All of these 3 big ports I'm not using. The RE port I'm using for the front panel inputs, so you've got the buttons and the potentiometers. I also didn't do a very good job at checking which pins are meant for what, so these 2 RF0 and RF1 inputs that the audio goes to, they're not analog inputs, so I've had to add some jumpers to pins that are. Then you can see on the analog input, I've got it referenced to ground. That should hopefully help with noise a bit, although you'll see in a bit it's still not that good. Then we capacitively couple it and shift it up with these potential dividers to the middle of the ADC range. This could potentially be used for the inputs from a resolver as well. Up here on the right you can see the RJ45 connector, PGD, PGC, MCLR, ground and power. That's what you need to program the chip. Then HV sense is an output, digital output, just to show when high voltage is present. And then I've got 2 analog inputs that I said were for sine and cosine from a resolver, but they could be used for anything. Then here we've got some other inputs and outputs. Output to the buzzer to make it beep, that's not being used anymore. HV sense, so that's an input that says when HV is present. HV active is an output, and you can use that to turn on and off that relay. Heading down a bit you can see what I've put in one box and just called the H bridge. This is the way that I've wired each module. So I did this weird thing with 2 resistors to try and make a fake differential pair. Whether that's actually doing anything, I got no idea. And you can see I've put the MOSFET modules themselves on a different sheet, which we'll have a look at. But you've got bus in, each half bridge has its own dedicated capacitor as well. And you can see phase 1, 2 and 3. Scrolling down, this is what we have for each gate drive circuit. So the weird differential pair thing, Then that heads in. These are current limiting resistors basically for the LED and the gate drive, which is optically isolated. Here's the DC-DC split decoupling for the positive and negative outputs. There's our Zener to clamp the voltage, LED indicator with a 10k current limiting resistor. Gate drive minus goes to 0 volts, that's on the source. 4.7 ohm gate drive resistor connected to the output of the gate drive chip. This is the high voltage and low voltage detection circuitry, so I've done something weird here with a resistor and a Zener. So I guess the idea is that when the high voltage is there, you get 3.3 volts across the Zener, that then turns on this LED. And when the LED is on, which is when high voltage is present, it pulls this low, it looks like. That then turns off this MOSFET, which means this can go high, which then pulls this down, and this turns on the LED and the high voltage indicator. So, a bit convoluted, but it works. Then down here, this is the weird e-stop relay, which I'm not really using anymore. The idea is that it's latching, so there's no software or anything. You press the e-stop, this relay latches on and just turns everything off. And then finally, this is the buzzer, just turned on with a MOSFET. So let's start by turning it on. I'm going to flick the low voltage switch on the left, and you can see all the indicator LEDs have come on. So we've got 3.3 volt, 12 volt and 5 volt rail indicators. Then each one of these is for the plus minus 15 volt supply on the output of these DC-DCs. The LEDs are powered between the plus and minus 15 volts, so if one of them's dimmer, that might indicate that only half of one of the bipolar supplies has failed. You can also see on the front panel this blue LED's on, so I can turn that off and turn it on. And then I'll show you, this button is the one that is currently programmed to turn on the high voltage, so when I turn this on, there, that green indicator is showing that the high voltage relay is energized. There's no high voltage supply at the moment, so the red indicator's not on. But if I turn on the second power supply that's connected to the high voltage input, then the high voltage indicator comes on. And you can see when I turn it off by resetting the microcontroller, the relay turns off, but it takes a little while for the high voltage to discharge. But overall, yeah, it's quite nice hearing the clunking relay. High voltage on, relay off, high voltage off. But what's this output actually useful for? Well, first let's have a quick look on the scope at what it's doing. Now this output is very noisy, but that's because of all the switching and stuff that's going on, so if we ignore that and just take a look at the output, I've had to slow it down quite a lot in software so that we can see it. This is a probe across one of the output phases, and you can see it spends quite a while at 0 output, and then it goes up and does this weird double pulse thing. And this is basically the output that's created by space vector modulation. Basically it's just a way of getting 3-phase sinusoidal output and fully utilising the supply voltage, instead of just controlling each half bridge with a normal sinusoidal input, which doesn't fully utilise the potential of the full supply voltage. And you can clearly see how we're using PWM here. Here's our pulses, and we're modulating the width of them. That's pulse width modulation. So as I say, although it looks a bit weird, 3 of these, you put them together and trust me, it makes smooth sinusoidal 3-phase with variable frequency. So one of the knobs on the front, I can adjust the frequency, speed it up, slow it down. But what's 3-phase useful for? Well, by far the main thing is machines, or motors as most people like to call them. So here I've got the output of my inverter. 3 phases here, and they're going into this motor, which is an outrunner brushless DC motor from a remote control plane. And it's called outrunner because the rotor is on the outside. It's also known as an exterior rotor, and they're a bit weird really, but they're good for high torque and a few other things. It's also the beefiest motor I've got that I can pick up. So if I just hold this here and turn on the high voltage, let's see what happens. You can see it slowly turning. Nice. The reason it's turning so slow is because the frequency of that 3-phase that I showed you I was probing on the scope is pretty low. Again, I can turn the knob on the front of the inverter and I can speed up my motor. There we go, faster and faster. And that's as fast as my knob's going to let it go, so I'm going to go and put the code back to how it used to be before I needed to demonstrate the PWM on the scope. Right, now let's turn it on. There we go, that's minimum speed. And here you can see I can turn up the speed. It's going decently quick now. 3-phase output there. These motors are not actually designed to be driven by sinusoidal 3-phase. They're much happier with a sort of square wave kind of thing, because it's a brushless DC. And that's because of the construction of the windings. These are called concentrated windings. If you have something called distributed windings, instead of a trapezoidal back EMF, they have a sinusoidal back EMF, which then means you can have a sinusoidal input voltage. I have a motor on the way that has distributed windings, which means that it's designed for sinusoidal 3-phase, and that means instead of being a brushless DC motor, it's then a permanent magnet synchronous motor, which is a much cooler type. So there will be plenty of content on that once it arrives. Now, a problem with this type of motor is that it's synchronous, which means it will spin at the exact speed I tell it to, which is quite nice. And it will have some amount of torque at that speed, but if you need more than that torque, the motor will just instantly stall, as I can probably demonstrate. If I grab onto it, it's not slowing down at all, and then if I grab onto it too much, it just stops and starts shaking. Then to capture the speed again, I have to turn the frequency down until the rotor can get going, and then I can turn it back up again. The same also happens if I try to go too fast, so if I turn the speed up, the motor can keep up for a bit until, there we go, it stalls, because it doesn't even have enough torque to spin itself. Now that might make synchronous motors seem completely useless, but if you have some feedback coming from this back to the inverter, then you can make this pretty much the best type of motor. And for that you need rotor position sensing, which in high-end motors you might have something called a resolver, you might have a rotary encoder, you might have Hall effect sensors, or you can even just sense the back EMF on the motor, which is how low-end motors like this are intended to be operated. If you want to know more about that, I did make a video a year or two ago about a brushless DC controller I made, and I think I mentioned the back EMF sensing in that video. If not, and you want an explanation, let me know and I can maybe go into that. But this inverter is intended for open loop control, so there's no feedback, which basically means it's useless for synchronous motors. I can make them spin at a certain speed, but not with any decent torque. Don't let that fool you into thinking this inverter's useless though, because there's plenty of motors that aren't synchronous. For example, my personal favourite type of motor, the induction motor, and they're normally quite big, so this is an industrial one. And just for scale, the motor I was holding before, which is quite large, is tiny compared to this beast. This weighs about 40 kilograms, and it's 4 kilowatt, and it's very old, I think probably 80s. But just to show how far motor technology's come recently, this motor I was holding before is 3 kilowatt. 3 kilowatt, 4 kilowatt. Crazy. Now, I won't go into too much detail about the operation of induction motors. There's plenty of good videos already about that. But I will show off the fact that I can control it with my inverter. So, if I press the button to turn on the output, you can see the shaft starts to turn, which is quite nice. And right now it's spinning nice and slow. I still have speed control, so I can turn up the speed like this, and I can continue to turn it up. This motor's designed for operation on a 50 Hz 3-phase supply, but because I'm making my own 3-phase supply, I can spin it as fast as I want, really. The main limitation for me is that the windings on this motor are designed for 415 volt 3-phase, which is what we have here in Europe, but I'm only giving it 37 volts is what my power supply is doing. So that means I can't really overcome the back EMF at particularly high speeds. But I can still get it to spin faster than it's rated for. It's rated for around 1500 RPM, and if I get the speed setting just right, I can get it to do about 1700, which I'll demonstrate now. So this is what the white tape's for. This is my tachometer. Hopefully you'll be able to see the screen. Let's have a go. Yeah, you can see that. Just over 1700 RPM on a motor only rated for 1500. And as I say, this is only on a 37 volt supply, so could probably get it to spin quite a bit quicker. Not that I'd recommend that though, because it's not just electrical stuff that limits the speed, it's mechanical too, and you don't particularly want a 10 kilogram rotor exploding. It's got a lot of inertia, this motor. A scary amount. And now if I try and turn the speed back down, the motor will try and regen and my power supply cuts out, So pretty much the only way I can turn this off at this point is just to turn off the high voltage supply to the inverter, which is what I'm going to do now. And here it slowly spins down. But I wouldn't want to grab this, even now when it's not powered. There's just so much inertia in this rotor, it's crazy. And there we go, it's come to a nice stop. I didn't really explain, the white tape on here is because the tachometer needs good contrast so that it can tell every time there's been a full revolution. It comes with this fancy reflective tape, but I don't really want to use that, so white seems to work fairly well. Now, even though you can run an induction motor open loop, you can still make them perform a lot better if you have closed loop, so you get some kind of feedback on rotor position or rotor speed. And for that, a while ago when I was playing with this motor, I made this little adapter, so you can see it's 3D printed. There's a bolt here that sits inside, and the idea is that this goes into the threaded shaft, like that. Now you can see it spinning away. And then I also 3D printed this, so this is a Hall effect rotary encoder, and the idea is that that would just drop into there, bolt on there, and then that will give me accurate shaft positioning. It worked fairly well, but the circuit that controlled no longer exists, so unfortunately I can't demonstrate it, but I thought I'd show it anyway. Now there's one other thing I've used this inverter for while I've been messing around with it. I sort of hinted at it at the start, but let's take a look at the code and see what we could possibly use this for. So do excuse this code, it's a bit of a mess. I've been in a bit of a rush really. But there's not that much to see. I've been using MPLab Harmony, which is a bit like other IDEs like the STM one have similar things. And it basically just gives you a nice UI to show stuff. So these are the different peripherals. I've got PWM, I can configure everything here, so active high, active low, dead time, stuff like that. ADC, I can configure sample time, which pins I've got. I've got a timer which I'm not using at the moment as well. You can configure clocks, you can configure which pins are what, things like that, but the main thing to look at is the code, isn't it? So, taking a look at that, down at the bottom we've got our main loop. Initialize, that's just built-in stuff. The same with systasks. This whole thing's interrupt driven really, so the first thing I do when it starts up is wait for that black button, the leftmost black button, to be pressed. Then when that's pressed, we turn on the high voltage, and you can see that here, HV active pin. We're going to turn that on, take it high. Then here we have primary event callback register. So basically what I'm saying is when the primary event interrupt is triggered, run this function, which we'll have a look at in a minute. And this is PWM. The primary event interrupt is called once every duty cycle, basically. So I think I'm running at about 29 kilohertz. So this function runs about 29 kilohertz. And then we start our PWM. So let's have a look at this function that we call. There's a lot of stuff commented out. I can go through that in a bit. You can see we have two static variables here. We've got our angle and our speed. The speed is read from the potentiometer. So this is the leftmost potentiometer. So this is just ADC channel. The ADC is also triggered from the same primary interrupt. We're sampling at 29 kilosample per second. We're going to have a look at our ADC sample, which is 12 bits. Divide it by 100, that stops the knob from being too sensitive, basically. And then add 1 so that there's always some speed, even when the potentiometer reading is 0. Then we're going to increment our angle. We're counting up in tenths of a degree, so this line is basically just saying if we exceed 360 degrees, take off 360 degrees. And we do that every time we run. What these lines are doing is setting the duty cycles for the 3 half bridges, or the 3 phases. So you can see we have some kind of array here, which is in signlut.h, lut for lookup table. So here we've got a big thing. Here you can see the big load of zeros that we saw on the oscilloscope. And basically this is just 3,600 16-bit values. And we just index it with our angle and divide it by 16, which is 2 to the 4, because the PWM we're driving with a 12-bit resolution. That means we need to divide our 16-bit down to 12 bits. And that's for the first phase. Then the second and the third phase we need 120 and 240 degree offsets respectively. So we just add that. I'm still using the modulo operator again here, just in case when we add 120 degrees, if we exceed 360 we need to bring it back down. and again we divide that by 16. And for fixed frequency operation, it really is as simple as that. Just every time we run the interrupt, increment the angle a little bit, the electrical angle, and then update the duty cycles. This is all the code you need for a 3-phase inverter if you're running fixed frequency. But I said we were going to look at the code and see what we can change. So let's look at this stuff I've commented out and see what that does. What I'll do is I'll comment out what we've just used and I'll uncomment this. Mag. What's mag? Well, no, mag is not for Maggie, it's for magnitude. You can see we've got a 32-bit variable here, and we're reading an ADC. I wonder what that is. Well, that is our audio input. So we read that, we subtract 2048, and that should offset our audio. So instead of it being values from 0 to 4096, now it's a bit like it being signed. It goes from minus 2048 up to 2047. And that's our audio input, so with no phone connected or anything, it should be about 0. Next, we multiply it by another ADC input. This is our potentiometer, and that acts as our volume control. So when the potentiometer is turned down as low as it goes, that will be 0, and we'll have nothing on the output. Then we divide by 1024. That's basically, if I divided by 4096, then at max volume, we'd have the original input. But I also want to boost it a little bit. So the highest gain that this will allow for is a gain of 4. Then you can see the third phase we'll look at first. The duty is just locked at 0. For mono operation, we only need to use 2 phases. And then we've just got 2048, which is a duty cycle of 50%, plus magnitude and minus magnitude on the 2 phases, which sort of acts like a differential output basically, and just forms a full H bridge that directly drives the speaker. And this is a class D amplifier basically. It's that simple. Just swap some simple code for some different simple code and you've got a probably multi-kilowatt audio amplifier. So I can just plug in my headphone lead into the jack at the front. Now you could set this up for stereo operation. I've only got one speaker that I can test with though, so right now I think it's just using the left channel. So this lead runs off to a speaker I've got at the back that I showed in the previous video I think. And all I'm going to do is shove that into the first 2 phase outputs of the inverter. Then turn on the output and, oh, it's pretty noisy. It's interesting though, pretty much all of this noise seems to be coming from the phone, because hopefully you can hear that noise. If I pull the headphone jack out, a lot of it goes away. Yeah, I don't know if anyone knows why that is. Something to do with impedance matching is my first guess. But plug that in and then let's play. Ignoring the noise, it's very loud. And this should be good for probably a kilowatt output, which is quite a lot for audio. So yeah, unfortunately I can't play anything other than that because of copyright. But it's always a fun use if you've got some spare half bridges lying around. Play some music through them. Right, well, I hope you enjoyed that video. Should be back to the direct current control series soon. Just waiting for some bits to arrive. There were some unforeseen issues with the circuit I made for the next video. If you've got any questions about this inverter circuit, make sure you ask them in the comments below. I'm always here to respond and help. Thank you very much for watching. Don't forget to like and subscribe. And as always, until next time, have a good one.